The other algorithm for graph traversal is depth first search. And this is different from the breadth first search in that you would like to go as deep as possible by visiting the neighbors. And therefore, what you do is you select a route again, and then you do not visit every neighbor of the route, but you select one of them, and then you look at the neighbors of that one. And you go deep as possible until you cannot find any new neighbor to visit because they have all been visited. You then track back until you reach another vertex that has other neighbors. Okay, so the difference between breadth first search is in breadth first search, you want to visit all neighbors of your selected neighbor or vertex, and then recursively apply the same to each of those neighbors. But in depth first search, you select a neighbor, visit it, and then you select another neighbor of that vertex. So recursively, you go as deep as possible, and then you come back. So here are some examples. If E is selected as root, now the neighbors are again B, C, G, and H. Again, applying lexicographical order, I'm going to select B as my next neighbor. Now the neighbors of B are A, D, and E. E is already visited, but obviously, according to the lexicographical order, I need to select A anyway. And then look at the neighbors of A. They are B and C. B is already visited, so I need to go to C. Okay, and the neighbors of C are A, E, and F. A and E are visited, so I need to go to F. Again, the neighbors are C, E, H. C and E are visited, so I need to go to H. Then I need to go to I, the only non-visited neighbor. Then I need to go to G. Then I need to go to D. So this is the order you obtain by applying depth first search, starting from the root E with lexicographical order as the selection of neighbors. Or let's say you select A as your root, then the neighbors are B and C, so using lexicographical order, you don't need to, by the way, to repeat, you will select B, and then the neighbors of B are D, E, and A. A was already visited, so visit D. The neighbors are B and G. B is visited, so visit G. The neighbors are D, E, and I. D is already visited, so I need to select E. And the neighbors of E are G, B, C, H, so I need to select C here. And from C, you get F and H and I. You see, in breadth first search, the selection was propagating from the root to all the vertices in a balanced manner. But in depth first search, you try to go as deep as possible and then come back if you cannot find any vertex to process. In this example, again, let's do the final one. If H is selected as the root, and then the neighbors are E, I, and F. Again, applying the lexicographical order, you select E. The neighbors are B, C, G, H. H is already visited, so that's out of the question, but according to lexicographical order, you need to select B anyway. And then the neighbors of B are A, D, and E, so I need to select A. And then C, and then F. Now, the neighbors of F, C, and H, both of them are visited, so I need to come back. The previous vertex was C. And again, all vertices neighboring C, A, E, F are visited, so I need to come back again to A. Neighbors of A, B, and C are visited, so come back again to B. Look at the neighbors of B, A, D, and E. The only one not visited is D, so I need to go there. And then G, and then I. So this is how you apply depth first search. You see it's a recursive procedure. Okay, so let me also show you, if you select randomly, for instance, start from I as the root, and then G and H. Let's say I'm just selecting the next neighbor randomly. Let's select H. And then I'm going to select from E or F. Let's select E. And I'm going to select either G or B or C. Let's select C. At this point, I can select A or F. Let's select F. Now, at this point, all vertices neighboring F has been visited, so I need to backtrack to C. And the only neighbor of C that has not been yet visited is A, so I need to go here. And then I need to go here, the only one here, and the only one here. Okay, so this is how we apply depth first search. Now, we have seen two algorithms of graph searching. There are others, but these are the most prominent ones. And they are similar in complexity. In general, they require this many operations, the sum of number of vertices and the sum of the number of edges in the worst case. And sometimes you can also see the complexity expressed in b to power d, where b is the branching factor, or the branching factor is sort of the average degree of a vertex. In the case of breadth first search and depth first search, it's a little bit different. And d is the depth of the search. So this is the average distance between any two vertices. That may not be neighbors. So these are not straightforward to compute, but it's a general application where you can express the complexity of these in terms of these parameters. But in the general sense, they are similar in complexity, but they produce results that have significantly different characteristics. Breadth first search gives you a sort of balanced structure where you have a similar number of degrees across the edges and the vertices, but depth first search sort of tries to go as deep as possible, so you have long chains if possible, and the depth is going to be larger. Applications include robot path planning, again, a sort of a search on the topology, or topological sort, if you remember from partial orders, connectivity checking for graphs, bipartite checking for graphs, and planarity tests in graphs, because these are all related to the graph coloring, and you can assign colors as you visit vertices. For instance, with bipartiteness, you can perform a depth first search and assign colors alternatingly. And if you can find two partitions, you can conclude that you have a bipartite graph also. Or for instance, in artificial intelligence, you have puzzle solution and puzzle generation using graph searching, like mazes or Sudoku puzzles, and also minimum path, shortest paths, minimum hop, shortest paths, in case the cost of each path is equal, for instance. Or graph coloring is an application of graph searching in general.